Okay, so uh, last time we were studying about uh, different kind of heat engines, and we studied the analysis over the Brayton cycle. Okay, so a quick review of the Brayton cycle, which we were studying last time. So it's basically a gas turbine cycle. So we don't have any constant volume process within this cycle. Rather, we have constant pressure heat addition and constant pressure. We have constant pressure heat rejection. So what we do is that we replace the piston cylinder with the compressor and turbine. And so this is also known as the gas turbine cycle. Now in this cycle, we have a compressor, and then this compressor is connected with the combustion chamber, and then this combustion chamber is connected back to the turbine. So basically we have the fresh air that enters into the compressor, and the compression is done. Now if the compressor has no losses, we say that this is an isentropic compressor. Otherwise we can determine the isentropic efficiency of the compressor, or if the isentropic efficiency of the compressor is known, then we can determine what is the actual work input from the compressor. This is the same way as we discussed in chapter number 7. Then from the compressor, once the air is compressed, it enters into the combustion chamber. In the combustion chamber, it is mixed with the fuel, and then the combustion occurs. So basically, this is the heat addition process. This is the process where we supply Q in. Okay, and then from the combustion chamber, this hot air, which is pressurized, then it enters into the turbine, and the turbine goes through the expansion. And within the turbine, it goes through the expansion process. And so we have the work output of the turbine, but not all of the work output can be used. Rather, what we do is that we connect the turbine through a single shaft with the compressor. So some of the work output of the turbine will be used to run the compressor, and the remaining will be used as the work output from the whole gas turbine cycle. So we say this is the work net. This will be definitely less than the work out of the turbine, since part of the work of the turbine is used to run the compressor. And then we have the exhaust gases going out of the turbine. And this is how the cycle is completed. This is the actual cycle. In the idealized condition, what we do is that we replace the combustion and the heat rejection process by by heat exchangers. So the combustion process is considered to be a heat exchanger, where the Q in is going into the working fluid, and the exhaust is considered as a heat exchanger, where the heat is going out. Q out is going out to the from the system to the atmosphere. So the four processes that we have are the isentropic compression, then we have the constant pressure heat addition, then we have the isentropic expansion, and constant pressure heat rejection. We have two very important diagrams here. We have the PV diagram and the TS diagram. In case of the PV diagram, I have mentioned you before that in case of the Brayton cycle, we don't have any vertical line, since we have two constant pressure processes, constant pressure heat addition and constant pressure heat rejection. So they will be the horizontal lines, and then they will be joined together with an isentropic lines for the case of compression and expansion. On the TS diagram, we'll have two vertical lines, because we have two isentropic processes, isentropic compression and isentropic expansion, and they are connected together with the constant pressure heat addition and constant pressure heat rejection process. This is just the review of what we already did in our last class. Then I also mentioned that in case of the Brayton cycle, we have pressure ratio because we have a high pressure and we have a low pressure in the system. So high pressure divided by low pressure, that's the pressure ratio. Suppose if we know what is the pressure ratio, and uh, it is a process where we can assume the constant specific heat values, or we need to do the approximate analysis, or it is mentioned that use a cold air standard assumption. Then just by knowing the pressure ratio, we can directly determine what is the thermal efficiency of the Brayton cycle. But this is only for these cases. If we have to do the exact analysis, or we have to consider the variation of the specific heat with temperature, then we cannot use this formula. Sorry. Okay, the other thing that I mentioned before about the Brayton cycle is one of the limitation. One of the limitation of the Brayton cycle is that uh, we can do the combustion only to the extent that the temperature at the exit of combustion reaches or remains below the operating temperature of the turbine, because the turbine receives the combustion gases, and since the combustion gases are at a very high pressure and temperature, there is a possibility that the turbine might start deforming or melting. So we need to know that what is the working temperature of the turbine, and so this limits the amount of combustion that can take place in the combustion chamber. So the highest temperature is limited by the maximum temperature that the turbine blades can withstand. This is one of the limitation, and that limits the efficiency of the Brayton cycle. As we discussed before, also that the Brayton cycle can be used for the aircraft propulsion as well as for the electric power generation. For the aircraft propulsion, we need to add two more components into the basic Brayton cycle. So that makes it a new cycle, and we call it a jet propulsion cycle. We are going to study that by the end of this lecture. There is a back work ratio. Back work ratio is basically the ratio of the work of the compressor divided by the work of the turbine out. Since the turbine will be the one which will be using its work output to run the compressor itself, so we need to determine the back work ratio here as well. This was one of the examples that we covered last time. So we stopped at this point. So let's start from here onward. If anybody have anything to ask till this point, you can ask.
It's all good, sir. It's clear.
Okay, so how can we increase the efficiency of the gas turbine cycle? One way is that we can increase the turbine inlet. Okay, turbine inlet increasing means this is our turbine. So we can increase the turbine inlet temperature, but that means we need to do the more combustion. But again, this is going to be limited because the turbine has a specific operating temperature, and we can increase the temperature of the combustion gases, but it should remain below the operating temperature of the turbine. So by increasing the temperature of the turbine inlet, we can increase the efficiency, but there is a limitation of how much we can increase. So this is the first thing. We can increase the efficiency by increasing the turbine inlet. The second thing is that we can increase the efficiency of the turbo machinery components. So we have the turbine and compressor. These are the machines. And obviously in the real cycles, they will not be isentropic. Obviously in the real cycles, they will have inefficiencies. And because of the inefficiencies, there will be some losses from the turbines as well as from the compressors, and these losses will overall affect the performance of the gas turbine cycle. However, if suppose we employ these turbines and compressors uh, uh, from a good industry, which so that these turbines and compressors work very efficiently, then in that case it's going to overall increase the efficiency of the gas turbine cycle. The last thing is we can add modifications to the basic cycle, and this is what we are going to study in detail today. We can do intercooling, regeneration, and reheating. So we're going to study these things one by one. Okay, first of all, let's discuss about the actual cycle. When we talk about the actual cycle, when we talk about the ideal cycle, so ideal cycle has ideal components. So all components are working ideally, means no isentropic. Uh, so that means there are no losses. So let's talk about the processes. The first process is the compression process. The compression process, ideally, on a TS diagram, it should represent as a vertical line because the entropy should remain same. But when we talk about the actual cycle, so in reality, we will not have a compression process which has no losses at all. So in reality, it will not be an isentropic process, so the entropy is going to increase. So instead of having the process as 1 to 2 or 1 to 2s, we are going to have 1 to 2a as the compression process. So the dotted line represents the actual compression. Okay, then after that, from 2 to 3, in reality, ideally what we assume is that 2 to 3 should be constant pressure heat addition. But in reality, it will not be constant pressure, but there will be a slight drop in the pressure during the heat addition process as well. So the ideal process would be the solid line, but the real process would be the dotted line from 2a to 3. Then from 3 to 4, it's basically the expansion process in the turbine. Ideally, what we assume is that the turbine should behave ideally. There should be no inefficiencies in the turbine, so there should be no losses from the turbine. So the entropy should remain same, and that means it should represent as a vertical line on a TS diagram. But in reality, it should not represent as a vertical line. Why? Because there will be some losses and the entropy will increase. So when the entropy will increase, so it will not follow from 3 to 4s, rather it will follow from 3 to 4a. So that this will be the actual process, how it occurs inside the turbine. And then from the turbine exit till going out as exhaust, there will be some pressure drop in that process as well. So that pressure drop will also be there. So correspondingly, our actual cycle will be the dotted line. So this dotted line for the compression, then we have the heat addition, then we have the expansion, and then we have the heat rejection. So it's a little distorted as compared to our ideal cycles. Now, how do we introduce the actuality within the ideal cycle is by introducing the isentropic efficiency of the compressor and the isentropic efficiency of the turbine. Now, if you remember, we discussed about how to introduce the isentropic efficiency of the compressor and the isentropic efficiency of the turbine uh, if in case of the compressors as well as the turbine operation. We discussed this thing in chapter number 7. So for the case of the compressor, it will be H2S minus H1 divided by H2A minus H1. This will be the formula that we are going to use for the case of the compressor, since the compression is taking place between state point 1 and 2. And the turbine process is between point 3 and 4. So the isentropic efficiency of the turbine will be H3 minus H4A divided by H3 minus H4S. Now, how does these formulas came? We discussed this in a lot detail in chapter number 7, so I'm not going to repeat it again. But if you have any specific question relating to it, you can ask.
नहीं
Okay, so let's study a problem related to the gas turbine cycle. So we have a gas turbine power plant which is operating on an ideal Brayton cycle, has a pressure ratio of 8. So this is the pressure ratio, and this is RP. The gas temperature is 300 at the compressor inlet. So this is basically compressor inlet is 1 and its temperature is given 300 Kelvin. So we know that this 300 Kelvin is basically T1 and 1300 Kelvin at the turbine inlet. Okay, so turbine inlet, turbine is between 3 and 4. Since it is 1300 Kelvin at the turbine inlet, that means we know that it is T3. Utilizing the air standard assumptions, it's written air standard. It's not written cold air standard. The word cold is very important. So if it is not written cold air standard, it's just written air standard. That means it is the exact methodology. That means you have to use table A17. Determine the gas temperature at the exit of compressor and turbine. Okay, so the first thing is that we know 1 to 2 is an isentropic compression process. So T1 is 300 Kelvin. Okay, so what we can do is we can go into table A17. Okay. So at A17 we have T1 is 300 Kelvin. So corresponding to 300 Kelvin, we can determine what is H1. Okay, and we can determine what is PR1. So you can see here. So we can determine what is H1, what is PR1. Then after that, we know the pressure ratio. Pressure ratio is 8. So pressure ratio will be P2 by P1. So P2 by P1 is 8 here. Since we know P2 by P1, we know what is PR1. We can use this to determine PR2. So PR2 comes out to be 11.09. If we go back into the table, 11.09. So 11.09 would be somewhere between these two values. So we can determine what is T2 and we can determine what is H2 by interpolation. So this will be T2, this will be H2. Then similarly, T3 we know it is 1300 Kelvin, and since 3 to 4 is an again isentropic process, so we can use table A17. So from T3 we are going to get what is H3 and PR3. Then we know what is the pressure ratio. So pressure ratio here will be P3 by P4. We know what is P3 by P4. I'm going to use this thing and PR3 to determine what is PR4. And then we're going to go back into the table, and corresponding to PR4 we can determine what is T4 and H4. So the first part of the question was that determine the gas temperatures at the exit of compressor and turbine. Exit of pressure is state point 2, so T2 we already determined. Exit of turbine was a state point 4, so T4 we already determined. So part A is done. Is there anything within the solution of part A which is not clear to anybody?
It's clear here.
Okay. Now let's talk about part B. Part B says that determine the back work ratio. So back work ratio is basically what it is, the work of the compressor divided by work of the turbine. Okay, so work of the compressor, in case here we have compressor between 1 and 2, so work of the compressor will be H2 minus H1, and work of the turbine will be H3 minus H4. So it will be H2 minus H1. This is the work of the compressor. We already know what are the enthalpies, and work of the turbine will be H3 minus H4. Okay, so the ratio of the work of the compressor divided by work of the turbine will be the back work ratio. So that comes out to be 0.403. 0.403 back work ratio means 40% or 40.3% of the work output generated by the turbine is used to run the compressor. So that means the remaining work will be used to actually produce the electrical output. Then the next step is determine the thermal efficiency. Thermal efficiency will be W net over Q in. We studied in chapter number 6. So Q in here will be H3 minus H2. That will be Q in. It's a constant pressure heat addition. So we know what is H3, we know what is H2, we can determine what is Q in. We can determine what is the work net because we know what is work out, we know what is work in. Okay, so we can use this to determine what is the thermal efficiency of this Brayton cycle. So it's about 42.6%. Is this thing clear? Is there anything within the solution here which is not clear? Please ask.
It's clear, sir.
Okay, now suppose we have the compressor and the compressor was not behaving ideally. Rather, we have a specific compressor efficiency of 80% and we have a turbine efficiency of 85%. Suppose if we know what are the isentropic efficiencies of the compressor and turbine, then how this is going to affect the performance of the cycle. Then let's determine the efficiency of the cycle once again. So if we know what is the compressor efficiency, so we know that from the formula, the efficiency of the compressor will be the ideal work input divided by the actual work input of the compressor. So we already know what is the ideal work input. We determined it before. So if we divide by the efficiency of the compressor, we can determine what is the actual work input. And then if we know what is the actual work input, we can use here to determine that what is the actual enthalpy H2A. Because work of the compressor is H2 minus H1. But if it is ideally, it will be H2S minus H1. If it is actual, it will be H2A minus H1. So we can determine what is H2A here. And once we know what is H2A, then we can go back into the table and corresponding to H2A, we can determine that what is T2A. So what will be the temperature at the exit of compressor? Do you understand these steps here? This is important.
Sir.
Okay. Similarly, for the case of the turbine, we know that the efficiency of the turbine is actual work output of the turbine divided by the ideal work output of the turbine. Now we already know what is the ideal work output of the turbine. We just determined in the first part of the problem. Multiply by the efficiency of the turbine, we can determine that what is the actual work output of the turbine. So if we know what is the actual work output of the turbine and we know what is the actual work input by the compressor, then we can determine that what is the actual back work ratio. So we can recalculate it again. Similarly, we can determine that what is the heat input. Heat input was H3 minus H2, but now we are going to use H2A because this is for the actual cycle. H2A, we get it from here. Substitute the values, we can determine what is Q in. Then work net will be W out minus W in. We have the actual W out, we have the actual W in with us now. So we can determine what is the work net. So the overall efficiency of our cycle will become the actual work net divided by the actual Q in. So that will be about 26.6%. If you look here, ideally it was 42.6%. But now our efficiency of the gas turbine cycle reduced from 42.6% to 26.6% because our compressor and turbine are not working ideally and there are some losses of energy through the compressor as well as through the turbine. So by introducing the isentropic efficiency of the compressor as well as for the turbine, we can redetermine that what is the efficiency of the Brayton cycle considering those efficiencies. Similarly, we can also determine what is the temperature out at the exit of the turbine in the same way because we know that what is the work output of the turbine. So it is H3 minus H4. Okay. So, but now we know what is the actual work output. So we can determine what is H4A. Okay. So once we determine what is H4A, then we can go back into table A17 and corresponding to H4A, we can determine what is the temperature at the exit of the turbine. Do you understand this part of the problem? Is there any step which is not clear?
It's clear, sir.
Okay, so we introduce the efficiency of the compressor and turbine. Now let's discuss about how to increase the efficiency of the Brayton cycle in general. So first of all, efficiency of the Brayton cycle. When we talk about the efficiency of the Brayton cycle, so its efficiency is work net over Qn. So one way of increasing the efficiency is that if we reduce Qn, this is going to increase the efficiency of the cycle. Because Qn is in the denominator, if you reduce the denominator, so overall value is going to increase. So that's the idea where we actually introduce the regeneration. So let's first talk about what is regeneration. When we say regeneration, it means to regenerate something, to reproduce something, to reuse something. Okay, so basically what happened is that if you look into the cycle, this is our basic cycle. So in this cycle, we are supplying the energy at the combustion chamber, and this is our Qin. We are supplying it in the form of a fuel. As the fuel mixed with the air, combustion takes place and the heat is added to the air. Okay, now this air, which is high pressure, high temperature, goes into the turbine. Turbine produces the work output, and then the exhaust gases come out of the turbine. Now, interestingly, these exhaust gases are itself at a very high temperature, maybe around more than 500 degrees centigrade. 500 degrees centigrade is a very high temperature. Okay, so that means these exhaust gases, which are actually going to be wasted, going to go into the atmosphere, still have a lot of energy in them. And if we can reuse some of the energy from these exhaust gases, that would be regeneration. So this is the idea. We have the exhaust gases. Before going out into the atmosphere, what we do is that we make these exhaust gases to pass through a heat exchanger. Okay, so we put a heat exchanger here. Okay, and we make these exhaust gases pass through the heat exchanger before they go outside. Now this heat exchanger does what? It it has two air streams. One is the air stream of the exhaust gases. The other is the air stream of the new air, which is going from the compressor to the combustion chamber. Now this new air needs to have heat added to it. So instead of all the heat supplied by Q in through with the help of a fuel, what we do is that we make use of the heat of the exhaust gases and provide some of the heat from the exhaust gases to this cold stream, okay, to this new air. So now what will happen? All of the Q in which was required to be supplied to this air, now not all has to be supplied with the help of fuel, rather some of the heat is being supplied by the exhaust gases. And this heat which is supplied by the exhaust gases was eventually going to be wasted. But now we are reusing some of it, or we can say that we are regenerating it. So we are regenerating heat. Okay, and this regeneration of heat will allow us to use less amount of fuel to provide the same heat input into the into the working fluid, to the air. Do you get the concept or not? So we are reusing some of the energy which was about to be wasted.
Yes, sir. Got it.
Okay, so now the cycle becomes like this. Look at the cycle here. So we have the compressor. From the compression, from the compressor, compression is done, and then the cold air is then entered into the combustion chamber. But before going to the combustion chamber, it passed through the regenerator. So regenerator is our heat exchanger. Okay, this regenerator regenerates some of the energy from the exhaust gases and preheat the air going into the combustion chamber, and then this preheated air enters into the combustion chamber where we supply Q in, okay, with the help of a fuel, and then from the combustion chamber it goes through the turbine, and then after expansion the exhaust gases go out, but before going out the exhaust gases pass through the regenerator where they supply some of the energy for regeneration purpose, and then it goes out into the atmosphere. So now this becomes the Brayton cycle with regeneration. You have to understand one thing. The regenerator is an added component. The regenerator is an added component. It is a heat exchanger. It does not affect the compressor at all. It does not affect the turbine at all. The only thing that it affects is the combustion chamber. Why? Because all of the heat which was required to be supplied through the combustion chamber, now part of it is being supplied by the regenerator. Okay, so our Q in will actually be reduced. So we don't need to supply all the Q in by the combustion chamber. Okay, so basically, in case of the efficiency of this Brayton cycle, work net is not going to change at all. It would remain the same. The only thing that is going to change is the Q in, as the Q in is going to go down. And since the Q in is going to be reduced, so overall efficiency is going to increase. Do you understand the use of the regenerator and the regeneration process in the Brayton cycle or not?
Yes, sir. Got
Okay, now very important point is that we have a new component here. This component is the regenerator. And when we talk about the regenerator, so regenerator should have its own efficiency. And we call it effectiveness of regenerator. How do we determine the effectiveness of regenerator? Let's study the formulation for it. So first of all, you have to understand one thing. When we talk about the regenerator, so let me draw the regenerator here. Okay, so this is my regenerator. So in the regenerator, we have two fluid streams. One is the cold stream, which is coming from the compressor. So this is the cold stream. The other is the hot stream, which is coming from the turbine exhaust. So we have cold in, and then this cold in is going to get heat from the regeneration process, and so we will have cold out at the exit. Similarly, we are going to have hot in, okay, and then we will have hot, the hot stream is going to go out after supplying heat, so we'll have hot out. So we have one stream of cold air, so we'll have cold air stream going in, cold air stream going out, and the hot air stream going in and the hot air stream going out. So we have these four streams. We have these four state points, okay, uh, within the regenerator. So when we talk about the efficiency of the regenerator, so efficiency of the regenerator would be numerator over denominator. Okay, so in case of the denominator, it should always be the enthalpy of the hot stream going in minus enthalpy of the cold stream going in, because that is the maximum enthalpy difference. So this is basically what this is. This is delta H max. Okay, then when we talk about the numerator, so numerator, it should be delta H of any one of the stream. So if we are considering the cold stream, so it should be cold out, H cold out minus H cold in. If we are considering the hot stream, then it should be the H hot in minus H hot out. So here either it could be H cold out minus H cold in. Okay, or we can have, instead of this, we can have H hot in minus H hot out. Okay, so either we can use this one or we can use this one in the numerator. Both are okay. So these are basically what? These are the enthalpy difference of any one of the stream in the numerator. But in the denominator, we have the maximum enthalpy difference, so it should be hot in minus cold in. Okay, so suppose if you look here in this problem, okay, so we have 4 state points here. If I look here, so the cold stream going in is a state point 2, cold stream going out is a state point 5, hot coming in is a state point 4, hot going out is state point 6. Okay, so if I look here, so the efficiency I can write here in the denominator, it should be hot in minus cold in, so it will be H4 minus H2. Okay, and in the numerator I can use any one of them. Okay, so let's say if I use, for the case of the cold stream, so it should be cold out minus cold in, so it will be H5 minus H2. Okay, so this becomes the effectiveness of the regenerator. Or if I want to use the hot stream, then it should be H4 minus H6. So both, so these are the two formulas for the case of effectiveness of the regenerator. Do you understand how we determine this formula? How we develop the formula?
Yes, sir. Yes, it's clear.
Okay. So this is the effectiveness of the regenerator, H5 minus H2 divided by H4 minus H2. Okay. So on the TS diagram, or how the regeneration process is going to be represented. So this is our compression process 1 to 2. Then after 2, instead of going directly into the combustion chamber, first it enters into the regenerator. So we have Q regeneration from, let's say, 2 to 5. And then from 5 to 3, we have Q in. So our Q in is actually reduced. Previously it was 3 to 2, 2 to 3 was Q in. Now it is only 5 to 3 Q in. So Q in is actually reduced. And then we have our regeneration process here. Similarly, for the case after turbine, in the turbine, the process is from 3 to 4. So after turbine, we have it pass through the regenerator first. So this is the regeneration process. So from 4 to 6, and then from 6 to 1 is basically Q out. So Q in is reduced, Q out is reduced, okay, because of the regenerator, but it does not affect the compression or expansion process at all. So let's see. So let's see that this involvement in the actual gas turbine cycle in case of the regenerator. Okay, so we have the effectiveness of the regenerator using the formula for the effectiveness of the regenerator in the previous problem. We know what is H2A, we know what is H4A, we can determine what is H5. Okay, once we know what is H5, now we can determine Q in once again. Previously Q in was H3 minus H2A, but now it is not H3 minus H2A, now it will be H3 minus H5. Okay, so our Q in will be changed. So we are going to use this changed Q in into the main formula, and we will determine what is the new thermal efficiency. So it's basically 36.9%. So previously the efficiency of our cycle was about 26.6%, but by using the regenerator, the efficiency actually increased to 36.9%. Yes, anybody want to ask anything?
No, sir, it's clear. समझ आ गया.
Okay, so this was one way. One way was to increase the efficiency by actually working over Q in. By reducing Q in, we can actually increase the efficiency. The next methodology is by working over the work net. Okay, and this is done with the help of intercooling and reheating. Now, how does the intercooling and reheating work? We are going to discuss it in after 5 minutes. Please put your attendance in the comment box, and then we are going to restart back in 5 minutes.
Okay, sir.
Okay, so now let's start with our analysis of the Brayton cycle.
Yes, sir.
Okay, so what we discussed right now is that we can increase the efficiency of the Brayton cycle if we can reduce the Q in. Now here we are going to introduce another technique through which we can increase the efficiency of the Brayton cycle. But this time, instead of working over Q in, we are going to work over W net. Okay, so we are going to introduce the concept of intercooling and reheating, and then based on the intercooling and reheating, this is going to increase the W net, and as the W net is going to be increased, so the efficiency will be increased. So first of all, let's discuss about the first step, compression. Now we are talking about compressing a gas. Now whenever we start compressing the gas, what happens is that the pressure of the gas starts increasing, and because of the increase in the pressure, at the same time the temperature of the gas also starts increasing. Now when the temperature starts increasing, the gas automatically start expanding as well, because whenever you increase the temperature, the gas expands. And so that means what? An expanding gas, when you have to compress an expanding gas, it's you need to provide more and more work. The compressor needs to provide more and more work input in order to compress an expanding gas. Okay, and so the work input of the compressor increases significantly. However, suppose if while we are compressing the gas, at the same time if we cool the gas as well, then what will happen? The gas will be pressurized, but at the same time the gas is cooled, so it will not expand that much quickly. So the temperature would remain in control, and as a result, less amount of energy will be needed to compress the gas. Less amount of energy will be needed to pressurize the gas. So what we do is that instead of pressurizing the gas in one step or in one stage, we do intercooling in between. We do the pressurization of the gas in multiple stages, and between each stage we do intercooling. So the gas is, let's say that the gas, we wanted to compress the gas or the pressurize the gas from 1 bar to 10 bar. We don't do 1 bar to 10 bar in one step. Rather what we do is that we first enter the gas into the compressor in first stage, and let's say we compress it from 1 bar to 4 bar. And then once it is compressed from 1 to 4 bar, then we're gonna take the gas out and we're gonna pass it through the intercooler. The intercooler is going to cool the gas, going to reduce the temperature of the gas. So this gas volume is going to decrease, and then we're going to enter this gas back into another compressor, and then the rest of the compression is done from 4 bar to 10 bar. So we do intercooling in between. When you do intercooling in between, then what happens is that the amount of energy needed for compression reduces significantly. Okay, so this is one thing. In the same way, it happens in case of the turbine as well. The turbine has to reduce the pressure so the expansion process can take place inside the turbine. But when the pressure is being reduced, at the same time, the temperature of the gas is also being reduced inside the turbine. And when the temperature is reduced, the gas starts contracting. Okay, a contracting gas, when you have to reduce the pressure from a contracting gas, less work output is going to be reduced. Less work output is going to be produced from that. Okay, because you need a larger gas volume, or or a gas with a larger volume to actually produce a work output. Okay, so what we do is that while we are doing the expansion process, we don't do it in one step. So let's say that the pressure was 10 bar and we want to reduce the pressure from 10 bar to 1 bar. We don't do it in a single go. We first pass it through one turbine, and let's say reduce the pressure from 10 bar to 4 bar, and then after that we do the reheating so that the gas expands a little more, and then after that we pass it through another turbine, and then do the rest of the expansion process. So we do the expansion in multiple stages. Similarly, we do the compression in multiple stages, and this is going to actually increase our work output from the turbine and decrease our work input of the compressor. So overall work net is going to be increased. So this is the main idea. Let's look at it from the perspective of TS diagram. If we look at from the perspective of TS diagram, so we can have a look here. We needed to compress the air inside the compressor. Suppose if we were using one compressor only, then what will happen is that we will compress the air from 1 to 2 to directly from here to here, from low pressure to high pressure, like this. Okay, but in reality what we do is that we make the compression in multiple stages. So we make the air to pass through one compressor, and then after that we take the air out of the first compressor, take it into an intercooler where we have heat rejection, Q out. Okay, now this heat rejection process takes place at constant pressure, and then we make the air to pass through the other compressor and do the rest of the compression. Okay, so what we have done is that if we look here in the TS diagram, we have added this area in our work net. So this area would not be there if there was no intercooling, but we added this area with the help of intercooling. Now increasing the area under the curve means increasing the work net. So that means we are actually increasing the work net by doing the intercooling. Similarly, when we talk about the expansion process, suppose if we do the expansion process in one go, then in that case, our expansion process would look like this, from 6 to 7 until the low pressure. Okay, but now what we do is that we do the expansion in one step, in one turbine, then pass it through the reheater where the reheating is done, and we supply another Q in. Okay, so that's caused the reheating at constant pressure, and then after that we do the rest of the expansion. So if in practical what we did is that we added this area in our work net by reheating. Okay, so suppose if there was no reheating, then this area would not be there and our process would look like this. But because of the intercooling and because of the reheating, our work net is actually significantly increased because we have added this area as well as we have added this area in our cycle. Okay, so our actual cycle would look like this. Our actual cycle would look like this. So we have, let's say if we have 2 compressors and we have 2 turbines. Okay, so obviously whenever we have 2 compressors, so we will have intercooling in between, and when we have 2 turbines, so we have reheating in between. Okay, so we do the little compression, then we pass it through the intercooler, then we do the rest of the compression, then we make it pass through the regenerator, then we enter into the combustion chamber, then from the combustion chamber goes through the first turbine, we can say that's a high pressure turbine, then we pass it through the reheater, then we pass it through the low pressure turbine, and then after that it goes through the regenerator and out. So number of state points have increased, 1 to 2 to 3 to 4 to 5 to 6, 7, 8, 9, 10. Okay, so the number of state points have increased, but if you look here, the process does not become more complicated. Why? Because we are just increasing the work, but the procedure remains the same. Previously we were analyzing a single compressor. Now we are going to analyze 2 compressors, but the procedure of analysis would remain the same. Previously we were analyzing a single turbine. Now we will be analyzing 2 turbines, but the procedure of analysis would remain exactly the same. So the procedure is actually repeated, but it has not become more complicated. It becomes lengthy, but not more complicated. Okay, the intercooling and reheating is at constant pressure. Okay, since it is at constant pressure, so Q in here will be H8 minus H7. Q out here will be H2 minus H3. So it's as simple as that. It's just the difference in it. So if you look here, all the processes are just the difference in enthalpies. So if you want to know that what is the work input for the case of compressor, is H2 minus H1. For this compressor, it will be H4 minus H3. For this intercooler, it's H2 minus H3. Okay, for the case of combustion chamber, it's H5 minus H4. Okay, sorry, for the case of combustion chamber, it's H6 minus H5. For the case of this turbine, it will be H6 minus H7. For the case of reheater, it will be H8 minus H7. For the case of the second turbine, it will be H8 minus H9. Okay, so here all the for each and every component, if you want to know the whether what is the Q in or Q out or work in or work out, it's just the difference in the enthalpies that we will be dealing with. So the procedure has become a bit lengthy, but it is not complicated. It's the same procedure that we have been following throughout before. Okay, the other thing is that we need to, first of all, till here, everything is clear till here. Anything which is not clear to anybody, please ask.
Yes, sir. Could you explain this statement? The process is always in conjunction with regeneration. What does it mean in regards to this?
The process is?
So the statement that's written down there, the process is always in conjunction with regeneration.
Yeah, okay. The process is always in conjunction with regeneration, because normally the regeneration work over Q in, and this intercooling and reheating works over W net. And normally whenever the Brayton cycle is employed, we design the Brayton cycle to operate at the maximum possible efficiency. So maximum possible efficiency is only possible if you reduce the Q in as much as possible and you increase the work net as much as possible. So that's why the process always works in conjunction with regeneration to produce the maximum efficiency of the Brayton cycle.
Okay.
Okay. Now one important thing is that first of all, we have one thing as the overall pressure ratio. Okay, so overall pressure ratio would always be the highest pressure divided by the lowest pressure in the cycle. But we have multiple compressors and multiple turbines here, so there should be individual pressure ratio for each compressor and individual pressure ratio for each turbine as well. Now, how to determine that? First of all, let's talk about the compression part. If I talk about the compression part, then let me just, okay. So if I talk about the compression part, then RP is the overall pressure ratio, and it will be P highest over P lowest. In this case, if I look here, the highest pressure for this is the compressor part. The highest pressure will be the pressure at 4, and the lowest pressure will be the pressure at 1. So it will be P4 by P1. This will be the overall pressure ratio for the case of compression. Now, if I want to know what is the individual pressure ratio, okay, so because we have two compressors here, so individual pressure ratio, or you can say that RP, I will say here individual IM. Okay, so individual pressure ratio here for compressor 1, it will be P2 by P1. This should be the same as P4 by P3. And how much it should be? This should be equals to overall pressure ratio power 1 by N, where N is the number of stages. Since we have two stages of compression here, so N will be 2 here. Okay, so here N is number of the stages. Okay, so if first of all, P2 by P1 should be the same as P4 by P3, and whatever the overall pressure ratio, P4 by P1, if we take power 1 by N, where N is the number of stages, we're going to get what is the individual pressure ratio. Is this thing clear or not?
Yes, sir. Yes.
Okay, the second thing is that in the same way, this was for the case of the compression. In the same way, this should be for the case of the turbine as well. Again, for the case of the turbine, we'll have RP, overall pressure ratio, is the highest pressure over the low pressure. Okay, so the highest pressure would be at the start of the first turbine. It should be P6 by lowest pressure will be at the exit of the last turbine. It should be P9. So P6 by P9. Okay, so this is RP. Okay, and then we can determine what are the individual pressure ratios for each turbine. Okay, so RP individual, it should be, so it should be P6 by P7 for first turbine. This should be the same as P8 by P9 for the second turbine. Okay, and this is equals to what? It is RP overall pressure ratio power 1 by N, where N is the same as the number of stages for the case of the turbine. Since here we have two stages of the turbine, so N will be 2. Okay, so RP is the overall pressure ratio. And remember, overall pressure ratio for the case of the compressor and for the case of the turbine will be the same. Okay, so RP for the case of compressor, overall pressure ratio for the case of the compressor will be the same as overall pressure ratio for the case of the turbine. Okay, so this is the idea. Okay, so this is the methodology through which we are going to determine the individual pressure ratios, and we can actually relate it with the overall pressure ratio for the case of the Brayton cycle. Anything which is not clear so far?
It's clear, sir. Yes.
Okay, so let's see the problem here. We have an ideal gas turbine cycle with 2 stages of compression and 2 stages of expansion, has an overall pressure ratio of 8. So the overall pressure ratio is 8. So this RP is 8. Air enters each stage of compressor at 300 Kelvin. So it's T1 and T3, both are 300. And each stage of turbine at 1300 Kelvin. So turbine entering is at 6 and 8. So both 6 and 8 is 1300 Kelvin. Determine the back work ratio and the thermal efficiencies of the gas turbine cycle, assuming no regenerator and an ideal regenerator with 100% effectiveness. So let's start solving the problem. First of all, let's determine the individual pressure ratio. So we have one compressor here, P2 by P1, other compressor P4 by P3. So P2 by P1 should be equals to P4 by P3 should be equals to overall pressure ratio power 1 by N. Here, since we have 2 stages of compression, so 1 by N will be 1 by 2, so that will be 8 under root. So that will be 2.83. This is for the case of the compression. For the case of the turbine, P6 by P7 should be equals to P8 by P9. This should be equals to, again, 8 under root, so that's 2.83. Is this a step clear or not? Is this a step clear or not?
Sir.
Okay. Okay, so the next thing is that here in the question, since nothing is mentioned, so we are going to use the exact analysis. Since it is not mentioned, that use the approximate method or use constant specific heat or cold air standard assumptions. So obviously we're going to
Yes.
use the exact methodology. So that will be table A17 that we will be using. And we know for table A17, everything depends upon temperature. So if the temperature is same, so the enthalpy would be same. So we have, if we're saying that T1 and T3 are same, so obviously H1 and H3 will be same. If we are saying T2 and T4 are same, then H2 and H4 will be same. If you're saying T6 and T8 are same, then H6 and H8 are same. Similarly, T7 and T9 are same, then H7 and H9 are same. So first of all, determining this thing. Now let's move over to the solution. First of all, we know what is T1. T1 is 300 Kelvin. We're going to go into table A17 corresponding to 300 Kelvin. We can determine what is H1, and then we can determine what is PR1. Then we know what is P2 by P1. Since we know what is P2 by P1, then we can actually determine what is PR2, and then corresponding to PR2, we can go into the table and we can determine what is T2 and H2. Similarly, for the case of the turbine, we can analyze one turbine. So we have T6 is 1300 Kelvin. Corresponding to T6, we can determine what is H6 and PR6. Now we know what is P7 by P6. So we can use the PR6 and P7 by P6 to determine what is PR7. And corresponding to PR7, we are going to determine what is T7 and H7. Going back into the table. Now we can determine what is the work of the compressor input. So it's basically two compressors. Both will have the same input. So we just consider the work or input of the one of the compressor multiply by 2. So here we have H2 minus H1 multiplied by 2. So it's give us what is the work input of first compressor. Similarly, we can determine the work of the turbine, but we have two turbines. Since both the turbine will have the same work output, so we can just determine the work output for one of the turbine and multiply it by 2, and we can get the overall work output of the turbines. Based on that, we can determine what is the work net from the cycle. We can also determine Q in. Now here just one thing to be noted is that the Q in will not just be from the combustion chamber, but rather the Q in will also come from the reheater. Okay, so for the combustion chamber it is H6 minus H4, but for the reheater it is H8 minus H7. So we have to add them together. So H6 minus H4 plus H8 minus H7. So that's the overall Q in for the system. So it's going to give us the total Q in. Once you have the Q in, work net, all these things with us, then we can determine what is the back work ratio, and we can determine what is the thermal efficiency of the cycle. So is this part clear? Is there anything which is not clear within the analysis? Just let me know.
It makes sense, actually. Okay.
Part B, I want you to go through it yourself. This is just employing a regenerator with 100% effectiveness. So when you apply the regenerator with 100% effectiveness, so it will not be H6 minus H4, rather Q in here will be H6 minus H5, because H5 minus H4 will be covered by the regeneration process. So there is a regeneration process here. Okay, so our Q in will be reduced. So now our Q in will be H6 minus H5 plus H8 minus H7. Okay, so this is by employing 100% effectiveness of the regenerator. Obviously, you're going to use the effectiveness of formula for the effectiveness of the regenerator to determine H5. So this is the same way as we did before. So I want you to go through it yourself, and this is going to increase the efficiency of the Brayton cycle. So with this, our Brayton cycle is finished. Now the next is the ideal jet propulsion cycle that we are going to discuss. If anybody want to ask anything regarding the Brayton cycles and the modifications that we made to increase the efficiency of the Brayton cycle, you can ask.
No, sir, it's all good.
Okay, so let's have a break of 5 minutes, and then we are going to start this last topic for chapter number 9, which is ideal jet propulsion cycle. Okay.
Okay.
Okay, so the last cycle is the ideal jet propulsion cycle. We are going to study. It is basically the cycle which is used in the jet engines, in the aeroplanes, rockets, most of the time. And again, for the case of the ideal jet propulsion cycle or the jet propulsion cycles, our main objective is not to produce power. Its objective is to produce power, but not in the form of electricity or the rotating power, but rather in the form of transportation. Okay, so whether it is the jet engine used on the airplane or for the case of the rocket, the main objective is to deliver or transport uh, from one part to another part, from one place to another place. So that's the main idea, and here we are using the jet propulsion cycle, and which is very close to the Brayton cycle. But since the Brayton cycle has the compressor and the turbine and the combustion chamber, and it's primarily meant to produce the electrical work output, and here we don't need the electrical work output, so we need to modify it a little, and we modify it a little by introducing some components that we studied before in chapter number 5 as well. And by using those components or introducing those components into the cycle, we actually make the cycle in a way that we do not want to produce the work output as electrical work output. Rather, we can produce the propulsive power. Here, what we need is the propulsive power, because we need the high velocity jets going out of this engine, and those high velocity jets going out of the engine provide the enough propulsive power for the jet engine to move forward. So this is the main idea. So we use this in aircrafts, we can use it in the rockets and things like that. So the idea is that we have a Brayton cycle. If you remember, in our Brayton cycle, if when we draw it on a TS diagram, okay, so we have isentropic compression. Okay, so we have isentropic compression in the Brayton cycle. So here we have the compressor. Okay, then we have the heat addition in the same way like we have in the Brayton cycle here. Then we have turbine. Okay, so this is turbine. Okay, but here the compressor and turbine are not intended to produce the work output. Rather, the turbine is designed such that it provides the work output just enough so that it can cover the needs of the compressor. So work net here is actually zero, because we don't need the work net in that format. Rather, what we do is that we produce the high pressure and high temperature gases that we then need to pass through another device which is known as nozzle. Now we couple the nozzle with the turbine, and nozzle has an advantage we studied in chapter number 5, that it can convert high pressure energy into high velocity output. So this is what we need. We need high velocity jet at the exit. So we have the air entering into our jet propulsion cycle, and as it passes through all the components of the jet cycle, at the exit, what we need high velocity air going out. And when we have high velocity air going out, this provides the enough propulsive power for the jet engine to move forward. So we produce very high pressure and high temperature, and these high pressure and high temperature, when this gas after passing through the turbine enters into the nozzle is the one which is the key thing here that produce uh, that actually produce very high velocity jet, and this is our objective here. Our objective here is to produce high velocity jet, high velocity. Sorry. High velocity exhaust. Here also one thing is one another change is that in case of the compressor, we couple the compressor with another device which can increase the pressure, and that is known as the diffuser. Now, if you remember what we studied in chapter number 5, that opposite to the nozzle is diffuser, and diffuser is a device which can convert high velocity or high velocity fluid into high pressure. So it reduces the velocity, increases the pressure, exactly opposite to the nozzle. So normally this jet engine is used in aircraft, and on the wings you have the jet engine, and since the aircraft is moving, so the air entering into the jet engine is already at a very high velocity. So the first thing is that we convert that velocity into pressure energy, then we further compress it inside the compressor, and then after that we make it pass through the turbine, we make it pass through the combustion chamber where the combustion takes place, and the very high temperature and high pressure gases are produced. Those gases pass through the turbine is just enough to produce to run the compressor, and then after that it all of it passes through the nozzle, where the nozzle converts almost all of the pressure energy to the high velocity. And so we have the high velocity exhaust going at the exit of this jet propulsion cycle, and this high velocity exhaust actually provides the propulsive power which is needed actually as an output of this jet engine. Okay, so it's very similar to the Brayton cycle. Two components added: nozzle is added with turbine, and we have the diffuser which is added with the compressor. The reason of adding these two components is that the jet propulsion engine is actually used in aircraft which is already in motion. So we need to first convert that motion energy, kinetic energy of the air going in to pressure energy, then further make compress it, and then produce the combustion, and then combustible gases needs to go out, and so we need to add nozzle to it so that the combustible gases while going out converts all of the pressure energy into high velocity exhaust. So this is the main idea of the ideal jet propulsion cycle, very similar to the Brayton cycle but with a little modifications into it. Okay, is there anything which is not clear? Please ask. Are the steps of the ideal jet propulsion cycle clear to everybody or not?
Yes, sir. All of it is clear.
Okay, so the processes are we have four isentropic processes here, and then we have two constant pressure processes. The first is isentropic compression in the diffuser, then we have the isentropic compression in the compressor, then we have the heat addition in the combustion that will be in the at constant pressure, then we have isentropic expansion in the turbine, and we have isentropic expansion in the nozzle, and then we have the heat rejection which is again at constant pressure. So once we have these things, we can determine the propulsive power. If we know what is the velocity at the main thing would be to find out what is the velocity at the exit of the nozzle. So this is going to give us the propulsive, the thrust. Well, when you multiply by the velocity of the aircraft, that's going to give us the propulsive power. And once you have the propulsive power and we know what is the energy input that we are supplying, so we can determine what is the propulsive efficiency of this jet engine. So let's have a numerical associated with it. So we have a turbojet aircraft that flies with a velocity of 260 meter per second. So that's the velocity with which the jet aircraft is moving. So this is the velocity of the jet. At an altitude where the air is at 35 kilopascal, so that's basically P1, and the temperature is minus 40 degrees centigrade, that's basically T1. The compressor has a pressure ratio of 10, so that's RP, and the temperature of the gases at the turbine inlet is at about 1100 degrees centigrade, so that's basically T4. This is the turbine inlet. Air enters the compressor at a rate of 45 kg per second, utilizing the cold air standard assumption. So we have to utilize cold air standard assumption. That means we cannot use stable A17 because we have to use the cold air standard assumption. Determine the temperature and pressure of gases at the turbine exit. Okay, so turbine exit is here, state 5. So we need to determine what is T5 and P5 at this point. And the velocity of the gases at the nozzle exit. So nozzle exit at 6. So we need to find what is the velocity V6. And the propulsive efficiency of the cycle. So let's start analyzing one by one. So let's first start with the first process 1 to 2, which is an isentropic expansion in case of diffuser. So we have a diffuser here, the isentropic compression in the diffuser. So we analyze the first law of thermodynamics for the case of diffuser in chapter number 5. We are going to use the same formulation. The only difference is that since we are saying this is isentropic, so isentropic means Q will be 0 because isentropic is the same as adiabatic. So if you analyze it in the same way as we discussed in chapter number 5, putting Q is equals to 0, we're going to come up with this formula. So here, remember one thing, since the diffuser is a device which converts kinetic energy into pressure energy, the velocity is reduced significantly. So we can just imagine that we know what is the velocity at the inlet of the diffuser. That will be the same as the velocity of the aircraft itself, which is about 260 meters per second. Okay, so but the velocity at the exit of diffuser will be so small that we can just simply assume it to be 0. It's not 0, but it is so small then the inlet velocity that we can just assume it to be 0. So here, if we put V2 as 0, so we can determine T2. We already know what is T1. Now we know V1. We can determine what will be the temperature at the exit of diffuser. Okay, and then we can also determine what would be the pressure, because it is isentropic compression process. So when we have isentropic compression, so we have the isentropic formulas for between pressure and temperature. So we know what is T2, we know what is T1, we know what is P1, we can determine what is P2. So that will be the pressure. So the inlet energy, which was kinetic energy of the air entering into the jet propulsion cycle, the first thing the diffuser does is that it converts all of the kinetic energy into pressure energy, and so the pressure is increased to 56.4 kilopascal. The next step is process 2 to 3. It's again isentropic compression, but this is inside a compressor. So here we know what is the pressure ratio. Since we know what is the pressure ratio, so we know that how much will be the amount of pressure raised by the compressor. Just multiply by the pressure ratio, so we can determine what will be P3. This will be the same as P4. And then we can use the relationship between temperature and pressure to determine what will be T3, since it is isentropic process. Let's talk about two more isentropic processes. One is the isentropic expansion in the turbine. But for the turbine, as I have mentioned before, our main objective is not to produce the work output. So the total work net is 0. When we are saying that the work net is 0, that means the work out of the turbine will be the same as work in of the compressor. Okay. So when we're saying that work net is 0, that means work out of the turbine will be the same as work in of the compressor. We already know what is work in of the compressor, so we can determine what is work out of the turbine. So it's basically H3 minus H2 will be the same as H4 minus H5. Or we can write here CPT3 minus T3 equals to CPT4 minus T5. Just substitute all the known temperatures, so we can determine what is T5, and then corresponding to T5 we can also determine what is P5 using the relationship, isentropic relationships between pressure and temperature. Then we have isentropic expansion of ideal gas in a nozzle. Again, in the nozzle, this is isentropic. Since it is isentropic, so it will also be considered as adiabatic, so we'll consider Q0. So we will do it the same way as we did in chapter number 5. We will analyze the case of a nozzle with Q equals to 0, and we're going to come up with this thing. Now here again, the velocity at the exit of the nozzle will be so high, it will be so high that we can just consider the velocity at the inlet of the nozzle equals to 0. It is not 0, we can just assume it to be equals to 0 because it is very, very small compared to the velocity at the exit of the nozzle. Okay, so uh, we can use this approximation, and we can determine that what will be the velocity at the exit of the nozzle. So the velocity at the exit of the nozzle comes out to be like about 1007 meter per second. Once you know velocity at the exit of the nozzle, we can determine what is the propulsive power, and then once we know that, we can determine what is Q in. Q in is m dot cpt4 minus t3, and once we have the propulsive power and Q in, we can actually determine that what is the propulsive efficiency of this jet engine. So this is the solution of this problem. Is there any step, anything which is not clear within the solution? Please ask. Everything is clear so far?
Yes, sir.
So anyways, this is the summary sheet where you have all the formulas and the PV, TS and PV diagrams for all the processes that we studied in chapter number 9. And with this, our chapter number 9 is finished. You have some practice problems here in chapter number 9. The solution of the practice problems are already provided to you in the Google Classroom. So with this, we end our lecture today. Here, chapter 9 is done, and inshallah, next class we are going to start chapter number 10. So if there's anything anybody want to ask regarding this chapter, and any procedure, any step, any cycle, anything which is not clear, I'll be more than happy to answer. Okay, if everything is okay, so our class is done here. You can leave the class.
Okay, sir. Allah Hafiz. Eid Mubarak.
Eid Mubarak to you too.
Sir,
Yes.